Okay, you see my screen, right? Okay. So hello, everyone. My name is Anatoly. Today, I'd like to show you our work on data-driven fault seal uncertainty quantification. This is my content for today. I'll start with the motivation and why we think this work is important in understanding of petroleum systems. I'll show you the area of study and the data for such a workflow. Then I'll introduce Bayesian evidential learning workflow to you, which we use for uncertainty reduction, followed by conclusion and possible continuation of this work. In faulted areas, faults often play an important role in sealing our petroleum system. In this sketch, we have like 3 wells. One well number 2, is located on the horst and 2 on the downthrown part of the fault system. So the question is, can we use well data and predict column height in the hanging wall traps? So our most common approach for assessing sealing capabilities of the fault system requires a notion of shale gauge ratio, which is an average volume shale in the slipped interval. So how these can be used for quantitative estimation of column heights, or column heights which can be supported by these 2 faults. Typically, we use 2 methods. One is from Sperovic et al. 2002, and the other from Yielding 2010. The Sperovic method gives is based on core measurements of permeability in microfaults. And then they converted these permeabilities to capillary entry pressures for fluids, and they predict average capillary entry pressure. Yielding et al. Employed a cross-fault pressure difference pairs of wells and SGR data from several extensional basins. Later on, they derived linear equations which describe a maximum supporting pressure. And then we can convert it to the column of any fluid supported by this fault. So Sperovic, they both have some uncertainties and produce different results when applied. Sperovic algorithm predicts a column height of any size and drew unrealistic values. The image is just cropped. In Sperovic, the same SGR more than 20% can give huge range of different predicted column heights, like from 0 to whatever value. And they depend on 2 more variables, heavily dependent on maximum burial depth of the fault and the depth of the faulting. Yielding is controlled almost totally by SGR. As you can see from here, column heights of the same SGR are equal at small range burial depth up to like probably 2 to 3 kilometers. So there are linear equations which controlled by depth intervals above 3 kilometers, between 3 and 3.5 kilometers, in between 3, even below 3.5 kilometers. And they produce discontinuities in predicted column heights. So these lines actually. So a common approach is to estimate fault seal capacity is to define all the variables from these methods to use. Usually, and how these variables are chosen, usually using expert knowledge, literature data, geological analogs, or common sense, and to produce one or several deterministic scenarios of column heights held by the fault. So what can be these variables? So actually there are 9 of them. So the first is, usually we have our wells with the log data. Usually we use gamma ray data to convert gamma ray to the shale. There are several methods, linear, non-linear methods, many proprietary methods, or advanced methods, how we can do this conversion. Through vertical displacement along the fault, these 2 give us SGR, shale gauge ratio, which is not a variable, just a proxy, the amount of shale of the fault plane. Then it's up to us to choose which methods of getting capillary entry pressure to use from Yielding or Sperovic. If we're using Sperovic, it's good to know what is depth of the faulting, what is the equation of relationship between SGR, or Zmax and ZF plus SGR, and fault rock permeability. Then we can convert that fault rock permeability, if we know interfacial tension and contact angle between fluids, we can convert it to capillary entry pressures. From yielding, we get capillary entry pressures directly from data. And then using hydrocarbon density, we can get we can get the column height, which can be held by this piece of fault. Well, deterministic scenarios may include large uncertainties, may lack of understanding of uncertainty, and can be biased due to overconfidence in ability to estimate uncertainty. For example, in this made-up example, using different fault seal variables may create quite different column heights supported by the fault plane. Often, it does not even mean that we can use these values, as they can be larger than the thickness of the reservoir. So it doesn't mean that we can, and it's something what fault plane can support. But employment stochastic techniques around the most probable scenarios and utilization of data science methods can give less biased fault seal estimations and uncertainty quantification. Usually, we can utilize mean of probability, which is expected value from distribution, and our prediction could be less biased. Also, we have uncertainty estimation with variance from distribution. Thus, the main motivation for this work is to see if we can use data-driven methods to reduce uncertainties and effectively predict column heights at known location using both data, because we have lots of data along the well, and geological knowledge. Also, we can answer such questions as what fault seal variables are the most sensitive on predictions of column height held by the fault. One of the best regions in the world to study faults is Viking Robin. Viking Robin is late Jurassic, early Cretaceous graben system formed as a result of Atlantic opening. The black rectangle is a study area, and this picture represents the importance of faults in Viking Robin. You see the stratigraphically reservoir, which is here below source rock, but tilted fault blocks and the rifting system in general make it possible across fault migration. Thus, the Viking Robin accumulations are associated with horsts, footwall, hanging wall traps. AKBP kindly provided us with regional basin models and with fault and surfaces, and with 3D reservoir models, and with the well data of one of the recent oil discovery. So the oil discovery includes 4 wells, A, B, C, and X, which hit different fault blocks. Well A, C, and X have different column heights at the same stratigraphic level. Well B reported as dry. Our data consists of well A, C, and X. Well X on the upthrown part of the fault block, others are on the downthrown part. In this study, what we're trying to understand, so we used observed column height from well C and well log data from well C, as well as well log data from well A, and we want to predict, we want to predict fault seal capacity for this fault block from observations from well A, well C, and observed column height from well C. Well, we assume that fault seal has a major control on the column height between adjacent fault blocks. Also, we neglect spatial uncertainties here. So that means that this study is a 1D study, I would say. For this, we use a collection of methods. It's not like one straightforward method, a collection of methods termed Bayesian evidential learning, or BEL, for uncertainty quantification. BEL approach characterizes by 3 features. So first, it's Bayesian. That means it relies on a notion of prior knowledge. It's evidential, and evidence is provided from both observations and modeling. And it relies on some sort of statistical learning or machine learning, right? Well, we split BEL on 5 stages. First, we need to assign the distribution of initial prior, or of our fault seal variables, which I showed you on the previous slides. Usually we know them from expert knowledge or literature. Then we run Monte Carlo, or randomly selected value from prior distribution and number of times, and run our model calculation. The falsification technique is we're trying to understand if our observed column height is belong to possible prior model. So if not, then prior is, we can call falsified prior, and the model is wrong. And sensitivity, which parameters more sensitive or bring more uncertainty. And eventually we're running prediction. We want to predict column height under the evidence that we already have from well C and from well A. And we can report uncertainty reduction. So let's go step by step. First, we need to assign prior distribution to FaultSeal variables. So for example, for gamma ray to V-shell methods, we use 1 AKBP methods for conversion, and 1 linear to extreme nonlinear methods to convert gamma ray to V-shell. So that means that's a uniform distribution where numbers 0, 1, 2, and 3 correspond to conversion method. Then we use throw as a truncated normal distribution. That's what we get from geological model. The throw in the fault plane between well C and well X, and well A and well X. Then we use range of reservoir depth for well on downthrown sites, and methods we choose. 0 is yielding and sporovic is 1. And depth of faulting, which equation to use to convert SGRs to fault probability, and then antifascial tension, contact angle of the fluids. Well, we pick value from these from these distributions and do 5,000 realizations. All realizations are here. For well C, like all these lines are here, and for well E, all these lines are here. To be more specific, these lines are column height that can be supported by the fault using our prior knowledge of distribution of FaultSeal variables. Some values are realistically high, but it's not a prediction. It's just all possible scenarios based on existing geological knowledge and stochastic simulations using established workflows. Here in yellow rectangles are reservoir intervals observed in well C. That means that we have observations here of 27 meters, 12 meters, 20 meters, and 20 meters here. And on well A, reservoir where we want to predict column height. And again, we're going to use all 5,000 simulations only in reservoir zones. So we're going to omit all of the simulations above and below and between. FaultSeal variables, all of these variables, they actually are reflected in all these simulations, on all these 5,000 simulations. And we can use these simulated models, all these 5,000 simulated models, as predictors, because actually all the uncertainties are there as something which we want to use to predict our final column height on. But there are too many of them. So we use PCA to reduce dimensionality. PCA can construct some new characteristics that turn out to summarize our data well. Of course, these new characteristics are constructed using the old ones, the FaultSeal variables. PCA combines our input variables in a specific way that we can drop the least important variables. So we choose 8 principal components of 8 vectors that can describe our data and which explain 95% of model variance. Then we use distance plot between principal components and distribution to check if our simulation model is falsified. So our observation point is here. So if our point was above this cutoff line, then our observation would not be described by our model, by our simulations. And we would need to revise our prior distributions or simulation strategy or make our model more complex. So this is the falsification step. We run distance-based global sensitivity analysis. It's analysis based on distance between different clusters. We ran it on sensitivity of PC components, principal components, and of FaultSeal variables. So we run it on PC components to understand if we have insensitive components. In that case, we would remove them from our next step from regression. As you can see, all our components are insensitive, so insensitive marked by blue color. So we're gonna use them all. We run the GSA and FaultSeal variables to analyze and visualize which parameters have little influence and which have high impact on overall uncertainty. It seems that depth of faulting is the only insensitive parameter. The most influential are methods of obtaining capillary entry pressure, either methods using yielding or sporadic, and conversion methods of gamma ray to shell. DGSA shows relative sensitivity between parameters, and it does not imply that the other parameters are not important, and they may bring lots of uncertainty and difference, but in combination, exactly when we use these two methods, it seems that these two pieces are the most important. So then we run canonical calibration analysis, which is multivariate analysis of correlation between simulated data and principal components. And after that, we run Gaussian regression and represent in histogram our prior model, which is blue, and posterior model, which is red. The values on x-axis may not seem very representative, as for you, they may not reflect any geological meaning, but similar to principal component analysis, it's a way to summarizing our data in a statistically more efficient way. So they represent all our 5,000 simulations, and we see the really dramatic, big, significant reduction of uncertainty for component number 1, as our distribution is less broad, it's really narrow. Also on the right plot, we see the principal component space, and again, the blue is prior and it's really scattered, with prior knowledge, and red is posterior. So we can observe how prior points are scattered again and posterior more concentrated. So we can report that the uncertainty is reduced here. Well, this slide is probably the main slide which summarizes a combination of geology and data-driven workflow. So on the right, we can observe uncertainty reduction when we see on histograms. Everything converted from PCA to column heights already, which can be supported by the faults. So mean of all points here, the predicted reservoir, which is a prior distribution, and posterior distribution, and prior distribution is here. The posterior distribution up to 200 meters and prior up to 500 meters. But these are all points from 5,000 simulations. Picture on the left is a random sample. So you remember all the 5,000, many lines. So random sample of one of these lines is here, it's a prior. And random sample of our posterior distributions is here. This image is the mean of distributions. So mean, so we can predict from our distribution using mean. This is the mean of prior. That's how our 5,000 points are looking like, is the mean of them. And this is the mean from posterior, which is red. And this image is the real column height observations from the well A, and yellow are reservoir zones, reservoir rock. We can see that posterior prediction here is something like around 40 meters, and the observed column height is 34. And here we see decline, and observed column height is 23 meters. But model was unable to predict dry intervals here and there. But we can see the kind of a decline and how column height prediction is going towards less values. So it seems that we are able to predict better column heights than our initial guess using prior knowledge. Well, as a conclusion, we combine geological knowledge and data-driven methods to do uncertainty reduction, and so we tried to predict column heights using 1D data. The most sensitive fault-sealed variables of methods of obtaining capillary entry pressure or methods of converting gamma ray to shale. Study fails to predict dry intervals, and definitely additional data would help to improve model accuracy, and this can be applied to other faulted areas. So in case you have like 2 wells and 1 fault between them with reported column height, we would be happy to use it. So, and definitely our one of our direction, also we're trying to use direct prediction using statistical learning and machine learning directly from our well logs and observed column heights, and to see any possible outcomes from that. How can we predict using machine learning methods fault column heights just directly from gamma ray or combination of well log data? Definitely one of our next step, which is currently going right now, is to run similar study in 3D. So where we want to introduce spatial uncertainty, because we have like several wells, and there is a distance from well to fault itself. So we are introducing spatial uncertainty by introducing uncertainty in variogram type, anisotropy, and azimuth. So all in all, we are running 3D models with the simulated fish shale. We already did it in Petrel. And then we're exporting our faults and running the same Monte Carlo with the same parameters that you saw before on the fault plane, on the fault surfaces. Then we combine all of that and convert fish shale to Petramod faces and export everything in Petramod. So it's looking like that. So we have fault capillary pressures, fault capillary pressures of the fault surfaces and permeability of the fault surfaces, and then we combine with the reservoir faces grid, and then we have 300 already different Petramod models with the variability on the reservoir lithology and distributions of the shale, I would say, and the different fault properties. But overburden, underburden, and boundary conditions are the same. So our plan is to run all the simulations and then export overlays like pore pressures, saturations, and kind of faces, and run not the same but similar analysis to predict column height accumulations or saturations based on prior knowledge. So, well, I think this is it. Thank you so much. Thank you all the industrial affiliates, and a special thanks to AKBP for very insightful discussions. And yeah, I would be happy to get any questions.
Okay, you have one question from the audience so far. I'll read that out. If you have other questions, go ahead and type them into the chat. So the one question that came in so far, Anatoly, is if an equation produces an unrealistic result, does it mean that the equation is wrong or that we applied it wrong? Did you hear that, Anatoly?
Yeah, I think yeah.
Okay.
Thanks very much for the question. I think that means that we need to apply it with we need to be very careful when we apply it, and we need to have lots of prior knowledge and understanding of like all the geological processes and everything in data in order to start to apply this equation.
So the equation might not, so are you saying the equation might not have a wide enough distribution for the prior, or
too
maybe
wide
not
distribution.
too wide, or not including perhaps the correct parameters to...
You know, if it is a statistical or empirical equation, all empirical equations have their range of validity. So we have to be careful. Are we violating the range of validity of that equation? If it's a physics-based equation, maybe it has some simplified physics. Maybe it's a linear elasticity. Maybe it is ignoring anisotropy. So depending on the context, it could be that we are violating the range of validity of that equation, or it could be that perhaps it doesn't incorporate all the physics or all the conditions. And so that's why it is giving unrealistic results. So it could be both. It could be the equation is wrong, or it could be that we are applying it wrongly.
Fabulous. We see one new message came in. Anatoly, how many realizations do you think it would require to adequately explore model space if you run in 3D and include spatial uncertainty?
So we have time constraint and really we need lots of time to run one realization. Now I'm running 300 realizations. So hopefully it's gonna be enough to start understanding whether we need more realizations, or it's at least like maybe sufficient to leave all these 300s. So, but definitely it should be not less than hundreds realizations.
Also, for Monte Carlo simulations, we have results that show that the variance of the prediction decreases as 1 over square root of n. So obviously in any kind of Monte Carlo studies, the more realizations you have, the better it is, obviously, but there are of course time constraints. But the variance goes down as 1 over square root of n. So we have that mathematical bound. And then there are other methods where we can explore, can we get the same uncertainty, but with fewer realizations? So we can project a few realizations and then see what the space of uncertainty is captured, and then we can select a few of them to compute full models. So there are methods where we can try to reduce the computational burden. But you're right, of course, any Monte Carlo methods, the more realizations we have, the better. And 100 is kind of a round number. We always go above, something above 100.
Thanks, Stepan.
Great, good. Okay, fabulous. We should move on to Tanvi Chida. So Tanvi